Pluggies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG, here with another episode of Ask Dave. This question comes from Jeff Angstitis. Unfortunately, he doesn't leave his call sign, but he has a very interesting question. He's a new ham operator, but has been around RF for decades. He says, regarding one-to-one choke balance, for all the construction info out there, I've never found any info about whether they present an inductive impedance or resistance. The answer is inductive. I understand that ferrites have U prime and U double prime properties. Usually directions are just to wind externs onto an FT240-31 core without any explanation as to why. My goal is to make a proper choke for just 10 meters. What is the minimum impedance for such a choke? Well, there are a number of things going on here. First of all, let's talk about coaxial cable. As you know, having been around RF for decades, what I'm going to show here is a typical piece of coaxial cable. This happens to be LMR 400. Now, you'll notice here that there is a center conductor surrounded by foam that is wrapped in aluminum foil right next to tinned copper wire. Okay? Now, it's excellent shielding, absolutely excellent shielding. So what happens with a coax is you've got the outer conductor like this, okay, and sitting inside is your center conductor. So this is usually held at ground level here on both ends, and then everything happens on the wire in the middle. Now, with well-shielded coax like this, what is inside the coax stays inside the coax. Now, the opposite happens too. If you have an external RF field that hits this coax, it will not penetrate into the center of the coax. So what happens inside the coax is a kind of special, well, I guess you would call it a special practical effect of RF in coax cables. Now, what happens on the outside? We've got to talk about this outside right here. The outside has got the inner surface, and we'll call that this blue right here, okay? And that's the inside, the blue surface. Here's the outer surface. Remember, we're dealing with RF, so skin effect is a thing. We can consider this a three-wire cable. The inside of the shield and the outside of the shield. Remember, skin effect, okay? So these are, the outside and the inside are separated from each other by a finite distance. And because of skin effect, the coax is flowing on the inside of the shield, all right? Now, the problem is when you get to an antenna, these are necessarily interconnected, okay? So you may have lots of good stuff happening here, and so the back and forth happens here, but the fact of the matter is this is practical. So you get a little back and forth here to oppose that. But if there is any kind of a reflection, I'll just draw a mirror here, any kind of a reflection, it's going to hit that outer part and come down the outside of the coax. Okay, so if you've got like a 10-meter antenna, which is 5 meters long or 2.5 meters on the side, so 15 feet long, so about 7.5 feet on the side, okay? Now, if this connects directly and you've got a one-to-one SWR, that's fine. But the problem is you can get current. It'll flow here. It will try to flow opposite that here. And it will hit this and it will want to go down the outside as well as the inside. How do you stop that from happening? You've got a problem. Because this can come all the way down into your repeater. This can come all the way down into your radio and cause issues. So what do? Well, we're dealing with RF, and in the case of 10 meters, 28 megahertz. Okay. That's actually pretty high frequency for this type of thing, a choke. Now, what you want to do is do something on the outside here to prevent this, and I'll call this a common mode current, because it has the attributes. We call this the common mode current coming down, and we want to stop it. Now, what will stop something at 28 megahertz? If you have an inductance like this, and you go on out like that, We know that the inductance is equal to, or the inductive reactance equals the inductance times the 2 pi f. In engineering terms, that would be L omega. Okay, but this is the inductive. The inductive reactance goes up with frequency. So up here, you don't need much inductance for this to represent a pretty good size loss for the signal. How much loss do you want? Well, if the signal comes down at the same strength as the one on the inside, you've got a problem. But let's say that this inductive reactance will reduce the signal on the outside of the coax by, say, let's see, 6, 12, 18 dB. Okay, that means that you've got a signal reduced by 3 S units. Okay, you can go for more if you want to, but 3 S units is pretty good. That's a lot better than having it equal strength to what's up here. So it doesn't take much at high frequencies like this to wind this a few turns around an inductor core, okay? You can actually just wind them, 8 or 9 turns like this. Notice I'm using a small turning radius. This is a small coax. This right here has a 4-inch bend radius, which is about that, 4 inches in. Okay, you don't want to bend that heavy cable much more than that. The littler cables like RG8X, you can bend a little bit more. Now, there is a problem with these cables which have this foam dielectric in that the inner conductor can migrate in there over a long period of time and might end up touching the outside conductor. So if you make something that small, beware that that's something that may befall you at some point and you'll have a short. But it takes quite a while for it to do that. So let's put this around here. Now, what are we doing? We are inserting inductance on the outside of the coax. You get enough in there to stop the common mode current. I should be more precise. Reduce the common mode currents to irrelevancy. Okay? 3S units down. You can go more than that if you want. It's not going to affect your system. Now, what are we making the coil of? This is a coil made up of the outer shield of the coax. Remember, what happens inside the coax stays inside the coax. Anything that happens outside the coax does not reach what's going on. So this will not affect the actual signal traveling on the inside of the coax, but it will present a severe impedance to what's on the outside of the coax. Now, there's a way you can measure that. There's a little piece of test equipment I picked up at Pacificon out in California, and it's put out by Halibut Electronics, and it's called a Common Mode Current Choke Test Rig. So what you do is you hook up your common mode choke with connectors. It can be N-type or PL259 or SMA or BNC, whatever you want. I normally use this because most of my system is made around these connectors. Collectively, the SO239 and the PL259 are called UHF connectors. And that's a very, very, very old name going back to the beginning of World War II when 10 meters was considered ultra high frequency. Anyway, that's changed. Oh, you can also disconnect it if it's like just a long wire, something like that. Then what this does on the other side is presents 2 terminals right here. These are both SMA. These you connect to your little nano VNA, okay? What's inside there is what's outside here. Now think about that. What's outside here is the outside of the coax. So what's inside the coax here and is measured by the VNA is what's outside on this. So you can measure this right here. And you can look with your nano VNA at how many dB down that signal is. And, you can get this thing in the range of what you need very, very easily. Now, I did a video very recently, and I'll put up on the screen here the number of that video so you can find it, where I demonstrated exactly such a test. Okay, so this is what goes on. You don't have to do much more. Remember, this will bring the common mode current signal down by 3 full S units. So if your regular signal is S9, you'll only see this as S6, and that will be way down. Okay? You can go for more if you want to, but that's about the practical limit because you start to get capacitance between the layers of the coil here, and that can throw things off. That's why we can measure it with this. So I hope that answers your question. You can just use air as your dielectric, or you can use a ferrite core, donut, toroid, and wind the coax around that a number of times. By the way, it's a lot easier to wind coax without the connectors on. So you may want to create a separate little one with connectors and use barrel connectors in your cable or something like that. There's lots of different ways of doing it. Are they effective? Yes. Now, what this also does is turn this into kind of like a one-to-one balun, because you put the thing through the choke and any coax or any common mode currents are restricted from going back. Or you can do the simple thing and just use this, which is an actual one-to-one balun. It's balanced to unbalanced. Okay, so it takes all the energy of the antenna and puts that on the inner lead in there, and the output is ground. Okay, that's unbalanced. These are about $30 from DX Engineering. I imagine other outlets have these for about the same price. Of course, we've had a lot of inflation lately, so don't be surprised if it goes up a little bit in price. Okay, so I hope that helps answer the question, and until we next meet, 73.